Hello guys, hope you're doing well. My name is Mahmoud and welcome to the new chapter of Special K. So the reason that I had a little bit of absence for the last couple of weeks was starting a new job. And after that, obviously, as you know, having a new job means a new responsibility, learning new things. And it was crazy. It was crazy. It kept for the past couple of weeks, and I can't say month. That's why I couldn't some kind of be there and record that many of videos. But the beauty of that is that actually I got a job as a transmission planner in my some kind of own province or in Canada, and it gave me a very good idea about my future path. The thing is that, as I just told you, I'm doing my PhD in electrical engineering. I'm also specifically in power engineering. So having this job that is completely related to my background and to my PhD is going to be a very blessing in my life. But also, I have this privilege to working with so many great people, so many some kind of advanced engineers in my field. And actually, I saw that how I can apply everything that I learned so far into the actual life. So for the past couple of subjects, we talked about electrical circuits, control, there's some kind of algebra and different kind of thing. But from now on, I would like to keep more focus on some kind of field and the courses that actually going to be replicate my background. And after that, obviously, it could be useful for you as well. That's why I thought it would be better to, rather than just having all of the courses beside the controls and other parts, I can start a new subject which is going to be related to the power engineering. So as you guys know, electrical engineers, they have different kind of fields. We do have the communication, electronics, power, and control. So power is going to be really important. Why? Because it's completely related to the power that you have inside your house, the outlets, anything that actually work, even the computer, even some kind of the data centers that you obviously heard about it, the AI and everything is need that much of power. And obviously that power is not going to be something around volts. We're talking about the kilovolts, and those massive values cannot be generated just by your house. It means that they have to be generated from far, far away. Then you have to move them with something that we call as a transmission. And then we need other kind of big machines that we know it as a transformers to step them down, and so many great facilities that actually at the end of the day will give you this privilege to just plug in and after that use your laptop computer and watch the video itself. That's why I'm trying to talk about the new subject that we already had it in our some kind of universities. But right now, from the point of view of the guy that actually working in this field, that gives me a great perspective of how actually we can apply that. Why do we need that, the power system force, and how we can use the electrical circuits to control and all of the subjects, even the algebra that we learned in the university, and do it in an actual job. Because in the future, if you would like to have any job related to your work, and most specifically related to your background, most specifically the power, they actually need to know that you have experience. Either you could get those experience from the universities, from the internship, from the actual job, or from watching the YouTubes that getting helps from different kind of expert that they would share their knowledge with you. So things that I understood in the past few years, that sharing is obviously caring, and by explaining everything is not just about my field. Everything I can learn more. That's why I started this subject. So this course is going to be about the power system 1 and power system 2, and probably is going to be more advanced power system that obviously could help you during the university stuff. And then in the future, hopefully, if you get a job related to the power, obviously you need it all the time. But just before that, let me talk about a little of my some kind of profession that right now I'm working on it, and it would give you a very good idea that why we actually need the power system. So without further ado, let's talk about it. As I just told you, the new job that I get, it has a name, and its name is going to be the transmission planner. So what does it mean by the transmission? We are going to actually talk about it. So this is going to be the transmission planning. So the thing is that when we're talking about electrical circuit, when we're talking about the power system, actually we're talking about a mega machine. It means that there's so many different machines that are connected to each other, using the cables. We don't have the wires anymore. Actually, we do have what is going to be inside those facilities and inside those machines. But those big and massive machines are connected by cables. By not just cables, it means that there are knowledge behind that. There are some kind of engineering, there are forecasting, and there are different kind of aspects that at the end of the day, you do have the outlet. Obviously, not everything is going to be so simple. So the transmission planner has this some kind of responsibility to make sure that it would connect your generator part, which is going to be the coal, gas, wind turbine, or can be any other kind of renewable energies from the source to your house. It means that that big line between the generation and after that you as a consumer is going to be the transmission job or the transmission planner job. Obviously, as you can see, it's not very simple just say that, hey, connect the cable and that's it. No, it needs forecasting. You have to consider all of the expenses. You have to consider the limitation. You have to come up with ideas at how actually at the end of the day, you can reach to the consumer or you can make a way from the generation part to reach to the consumer as fast as possible, simple, don't have any issues like a blackout or any outage. And at the end of the day, everyone would be happy. So as you can see, the transmission planning job is going to be considered as the 5 to 10 years of strategic master plan that is going to bridge raw energy generation, which we do have it in our power plants, to your wall outlet. And it's going to be ultimate puzzle to keep modern civilization running. Because at the end of the day, you would like to have a pure without any problem of the voltage, and actually you can connect anything that you want to the system. So before talking about anything related to the transmission, which is going to actually play its role over here in the middle, let's see what's actually transmission connecting from where to where. The very first thing that you have to know, we do have the source. Obviously, if you guys remember from electrical circuits, when you do have a circuit, when you have a closed loop circuit, you need a source. That source is going to be the voltage source, right? So in that voltage source, and after that, the voltage source could be the coal, gas, nuclear, renewable energies, and anything that you have beside yourself. Then these some kind of massive amount of voltage has to transmit, right? That's why we do have the transmission. If you just pass by the city, or if you see there's some kind of, not inside the city, by the way, in the roads, in the highways, you would see that the big, massive, some kind of construction site, that those guys actually are going to be as a pillars to hanging all of those cables that you can see over here, these cables on themselves. So this whole construction is considered as a transmission, and we do have it from 115 kV to 765 kV. And why we do have that, if I would like to give you a little bit of background, by the way, don't worry about any kind of concept that you are not very familiar right now, because as I mentioned, this is going to be the power system course. We are going to talk about it, but I'm going to give you a little bit heads up related to why actually we are learning it and how actually we are going to apply it in the future. If you guys remember from our some kind of electric circuits, or maybe probably you're in your university and doing some kind of power system work, P equals to V times I, which is very simple. It means that the amount of active power equals to the voltage times I. It means that if you do have the wire and if you would like to consider how much active power moved through that wire, you only need to multiply the voltage by I itself. So when we are talking about the generation, we are talking about the active power that these guys actually can produce. Obviously, we do have another form of active power, which is called as a reactive power. Right now, it's not very important. Let's put your focus on the active power, or the power that actually is doing its job, is doing something. So they're going to produce, obviously, from the coal mine, renewable energy generation, or whatever, and it has a voltage. And then that voltage also comes up with current, because multiplication of those values is going to be P. Another thing that we have to consider, as I just told you, when we do have the production from this side as a generator, we have to use the cable, which call it as a transmission line, which are going to be the big and massive cables, because when we are talking about those guys, they have to carry on the high amount of current. They have to carry on the high amount of voltage itself. So why we say that they have to be high amounts of voltage? Because in the coal line and on the subcon of the power plants, the voltage that they're going to produce the power is not that high. Actually, it's high right now in comparison to to 220 volts right now, but just consider it as something between, for example, 4 kilovolts to 25 kV itself, maximum. So when you're trying to move this amount of voltage throughout the kilometers of lines, another concept that we have to consider is going to be what? It's going to be Ri squared, which is a power loss. Obviously, when we do have a line itself, if you remember, when we had a wire, we had some kind of heat which is going to be dissipated because of the movement of current. The current is the movement of electrons, and if you do have those wires, electrons are going to fight against those resistance, or it would be better to say that those resistors are going to fight against the movement of electrons, and we do have the heat. Heat is going to means that the power loss. It means that whenever you do have the generation as the power over here, and the amount of power you get here as a consumer, obviously they're not going to be the same. And what is the problem? The problem is the power loss. So you can see over here that by having this amount of specific current, I'm going to lose a huge amount of power. I consider it as a power loss. Why? Because my V wasn't that kind of high, and obviously my I is going to be high. But what would happen if I can do something and increase this voltage? Increasing the voltage means that I is going to reduce as well. Why we're saying that? Because power is a number and it's going to be constant. It means that your power plant has this specific constraint related to the amount of power that it can produce. So obviously you cannot increase it as much as you like or decrease. At some points they do have also low limitation for themselves that we were talking about. So at the end of the day, the power is a constant number. So if you increase the voltage, one thing would happen is that current would increase. If the current would increase, you see that of the power or the power loss has the relationship with the power 2 of your current. If I increase it by 50%, I can, if I, for example, consider it by, if I some kind of reduce it by half, it means that my power loss is going to be there or be reduced by 75%. So that's why we are so eager to decrease the amount of current as much as possible. So maybe you would say that, okay, how I can convert this number, this is going to be considered as a small in comparison to 765 kV. How actually do that? We do have specific machine or big machines as transformers. Probably you all have seen that maybe in the cities or maybe in some kind of the outer parts. Mostly in the outer section, they're hidden inside some kind of maybe the tree or maybe the forest, not the forest itself, but behind the trees, because they are not very beautiful and they could make this scene a little bit ugly. But you also have seen it inside your house, because obviously when you're talking about increasing the voltage, we are also talking about decreasing the voltage. And at the end of the day, whenever we do have this amount of voltage, we would like to reach to something 120 volts or maybe 208 if you're talking about the line to line, and these transformers are going to play a big role. So we just understood that why actually we are trying to increase the voltage as much as possible, because at the end of the day, it has an advantage for us to reduce the amount of power loss. Reducing the power loss means that right now the efficiency is so high, and most of the power that I'm generating is going to reach to you as a consumer. And at the end of the day, I do have what? At the end of the day, I do have the distribution part. The distribution or the distribution planner actually is another some kind of job that is going to be highly related to the transmission planner. So if I would like to say it as a one way, transmission planner means that you're dealing with the voltage from 69 kV to above, and distribution means that you're dealing with the 25 kV and less. Distribution planner means that they're working inside the cities, and this transmission planner mostly working between the city and generator itself. So we talked about that one. We talked about everything that we had so far. But what is the company that I'm working for? So most of the time, whenever you're hearing some kind of electricity, when you're hearing about the energy, that most of the time is referring to electricity, you say that, well, you do have some kind of power organization. For instance, the place that I'm living right now is Nova Scotia, and we do have the Nova Scotia Power Engineer and Power. So when you're hearing about that, you say that, okay, this is a big organization. What is the big deal? Actually, no, because at some territories, at some provinces in Canada, rather than to having those some kind of, for instance, like NSPI or Nova Scotia Power, we do have another organization that they're going to work side by side of Nova Scotia Power or maybe any other kind of power departments, and those corporations call as ISO, or we call it as Independent System Operator. In Nova Scotia, we call it as ISO-NS, or Independent Energy or Electricity System Operator of Nova Scotia. Why we do have that? Because these organizations are going to work beside those power organizations, and these guys are literally focusing on the transmission planning, focusing on the renewable energies, and how those guys can actually be connected to the grid, while we're making sure that those guys are not going to be connected as they want. Those guys, they have to pass some kind of test. We have to some kind of see what are they going to do in the future, and then we make sure that those guys have all of those criteria and are not going to cause any harm to our system, because obviously those guys are going to be massive loads. We're talking about megawatts, hundreds of megawatts, and even connecting or disconnecting them from the grid could cause so much problem. So we, as an engineer or transmission planner engineer under the company that we call it as ISO, or Independent Energy System Operator, we are trying to make sure that everything is going to be safe and sound. We don't have it only over here. We do have it in Alberta. We do have it some kind of maybe in other kind of provinces, and even we do have it in the US itself, but not all the time. We do have this kind of independent organization. For instance, in the Quebec, because most of the time they're related to the hydro, we do have an organization called Hydro Quebec. So they don't have two different organizations. Everything is related to each other. And another important thing that we have to talk about is about this independent energy. Some kind of independent energy guys are trying to contact or try to be in touch with different kind of loads, and then by dealing or by passing some information from the clients to us and us to the clients, at the end of the day, we make sure that everything is okay. So enough is enough. So what we actually do, we do have 4 different kind of, actually it would be 6 in the future, maybe in the next slide, but I can talk about it in a very simple terms of 4 different responsibility that we do have. The very first thing is about the market master. It means that when you're talking about electricity, we are talking about the generation, transmission, and after that, reaching out to the consumers. But we also have to make sure that how we are going to categorize those amount of energy that is getting produced. Obviously, we cannot have all of the sources that are renewable energies because of some issues they have, because of the cost they have. So at some points, we still need those ancient ways or some kind of those fossil fuels ways in order to support us. So this is very important about marketing, and also when we were talking about the transmission planning, it's not just from the generation side to the consumer side, because at some points we do have the transmission between the provinces. So we also have to make sure while we're dealing with other provinces where we're getting the energy or importing or exporting energy, and at the end of the day, everything is going to make sense. Everything is going to be logical. Another thing that would be about architects, it means that we not only have to focus on the next year, we have to focus on 10 years, 20 years, or at some point in a long term of 30 years, that when we are dealing with a new load and we are dealing with some kind of new way of generation, we have to consider all of these factors, because again, we don't want to spend millions and millions of dollars and at the end of the day say that, okay, this is going to be feasible for maybe 5 years. So it doesn't make sense at all, right? And then we are also going to act as a guardian. It means that in the previous years, or maybe some kind of in the past couple of decades ago, we have just all of the loads that would be connected to the system and everything was fine. But after that, when we do have more consumers, when we do have more loads, means that no, we cannot just connect anything that we have to the system itself, because at the end of the day, those massive loads or maybe those not proper generational parts are going to cause so much harm for the system. Just imagine how frustrated you're being while you don't have the power for a couple of hours. Everything would be stopped, right? That's why it is our job to make sure everything is going to be guarded, safe, and sound. And finally, we have to some kind of have the coordination between the generators and utilities. Because one thing that you have to remember is that at all times, the amount of power that you generate should be as the same amount of power that you consume. Rather than that, any imbalance between could cause so much problem itself. If you just want to give you a very, very simple example that what would happen if us as a transmission planner are not going to take care of this kind of thing is that in 2003 in Northeast, they had a blackout, which 55 million people plunged into darkness. Because why? At that part, it was inadequate transmission infrastructure. What does it mean, inadequate amount in transmission infrastructure? I'm going to talk about it in the next slide. But I just want to tell you that this job, or at least this role, is going to be very important in our day-to-day life. So when we're talking about the transmission planning, we need a plan. We need a path in order to understand that what is the actual job is. That's why I made this part, which is going to be 6-step blueprint. The very first one is about the load forecasting. As I just told you, our job is not going to be only related to the next year or the next 5 years. It should be at least from the next 10 years to next 30 years and maybe more than that. And then we do have the assets generation. As I told you, it is so important for us to know that how much amount of power that we are generating and how much amount of power that is going to be transmitted and how much amount of power that you guys are going to consume, because based on that, we are going to say that, okay, system is safe. And then we do have the system studies. So obviously this all of prediction, this kind of forecasting and everything is not going to be meaningful unless we are doing some studies. That's why in the middle, we do have different kind of softwares that we are going to use that to make sure that while we are connecting the load or generation to the system, everything is going to be fine. Then we do have the constraint. Obviously, as I told you, all the time we are trying to make sure that we don't have any problem in the future. It means that we have to know our limits. We have to know the issues. And by us, or by the transmission planner, we are doing our studies to find those problems. And then we do have to develop a solution. So obviously, just prediction or just finding the problem is not the thing that we want. We have to offer a solution. Either we have to upgrade something, we have to move through a load from one point to another point, we have to contact with the consumers, we have to contact with the generation parts. We have to do so many things to make sure that everything match. And at the end of the day, obviously we have to see the cost benefit analysis. Obviously, we don't want to, again, spend millions of dollars, and at the end of the day, we see that we don't have that much of outcome out of it. As I mentioned, the very first thing that we are going to talk about is about the predicting the future. That's why in our company, rather than the transmission planner, we do have the resource planner. It means that the transmission planner job is actually doing the technical side. It means that when you go to the university, learn about some kind of different courses like the power system, you are actually using them in order to connect that knowledge to different softwares that I will talk about them just in very, very big picture. You guys can do your research about that. And then when we are making sure that everything is fine, we have to also have collaboration with other guys as a resource planner. So those guys actually doing the prediction, those guys actually talking about the marketing. And when we are doing the technical stuff, they're doing the marketing stuff and they're doing some kind of future work. So this predicting part is most related to the resource planner. It means that we have to see that what would happen in the future by using different kind of ways, by using different kind of mathematical ways, like machine learning, like econometrics and probabilistic forecasting, something that you know about and then you learn it in some kind of school itself, to guess exactly how much power millions of people will need in years from now, from talking about a couple of years to a couple of decades. So this means that we have to see about electrical vehicles, we have to see that the heat pumps and electrification. We also have to consider the GDP and population growth. And at the end of the day, we also have to consider the forecasting of the weather itself, which is going to play a huge role. Why a huge role? Because right now, the universe or some kind of all of the countries are trying to shifting their focus from the past, which was always the fossil fuels that obviously, as you know, they're going to cause so many issues. And also the most important one is about the pollution. But it means that those guys are going to cause a greenhouse gas emissions. And after that, we are going to damage the earth. That's why we are trying to stop that. We are trying to reduce it as much as possible. Obviously, we cannot get rid of it because we need that. Probably we'll talk about it in the future, but we don't need it that much right now. That's why we are trying to shift to the future. The future means that renewable energies, wind turbine, hydro dams, solar powers, or even the batteries themselves. So this juice, this some kind of generation comes when you have this massive shift from the past to the future, also is part of our job, because most of the generational part, or most of the plants that we are going to connect in the future, especially when we're talking about our province, because Nova Scotia has a plan to reach the 80% of renewable energies till 2030, it means that we have to come up with the fact that most of the time, at least 80% till at some point, at to 100% of the whole power should be generated by renewable energies. And that's a huge breakthrough. Obviously, that still has lots of challenges, but we are moving forward. So it means that the planner must map out what generation is being built and what is obviously dying. The ultimate catch. It means that the aging infrastructure is retiring fast. It means that all of those power plants that they were for a couple of decades ago, they cannot compensate, or they cannot tolerate this amount of power that we need because of the increasing the number of people, right? So it means that we need new sources and new renewable energy fluctuations also widely. What does that mean? It means that when we were talking about the wind turbine and the solar energy, obviously sun doesn't shine all the time and wind doesn't blow all the time. So we also have to find a way to mitigate that problem or mitigate that issue. Let's have a little bit step back and let's talk about a very, very fantastic law that we know, which is about the Ohm's law. It means that the voltage is equals I times R. It means that when we were talking about the current or the movement of electrons, we also talk about two other concepts. The voltage, it means that the source or the power or the energy that's going to causing the movement. And then we're talking about the resistance, the amount of some kind of force is going to fight against the movement of electrons. So if you would like to visualize it, we do have the voltage is going to act as a pressure valve, or is going to try to press this current to move through the wire, to cable through the line. And then we do have the current, which is going to be the water flowing through the line. And then we do have some resistance. The resistance means that these pipes are getting pressed because of some kind of materials that we do have inside the wire itself, and the current is going to have some kind of challenges to feed. But at the end of the day, we have to know the amount of power that we getting inject, or we some kind of injecting through to the wire, should be as the same as the amount of power that we're getting outside of that one. But maybe one of you would say that, okay, what about the power loss? The power out, when I'm saying that, the power out is going to be equal to the power that actually we are using, and plus the power loss itself. Another concept that worth mentioning is about the reactive power, because the reactive power is the invisible guy that actually make this pressure. Because when you're talking about this one, that is going to be the voltage and going to do the physical job, obviously you have also see some kind of pressure valve from the beginning that is going to move this some kind of piston, or move this some kind of physical part to, after that it can some kind of put pressure on the current, and after that go on, so on and so forth. So this guy is going to be reactive power. Why reactive power is not visible and it's not going to do actual job, but it's also important to us. But at the end of what, and another point, we also don't like it. Again, we talk about it in the future, don't worry about that. Another important thing that we have to know is about N-1 survival rule, or something we call it as contingency test. What does it say? It says that when you do have your some kind of infrastructure, that Megamachine infrastructure of the power, by the way, this is also part of our transmission planner job, you also have to make sure that if anything to happen to one side of one part of your system, a power plant, maybe a cable, maybe a breaker, maybe a fuse or anything, it has a fault in it, or maybe you're doing some kind of maintenance, your system still could manage the whole power transmission. Imagine that you do have the bridge, and after that, this bridge has three pillars. Why we're using three pillars? Because at some point you said, okay, two pillars is fine. Why we're using that? Because at the end, because if something happened to the middle one and this guy is some kind of destroyed, we're still going to have our bridge itself. Imagine that we do have lots of people that are just commute through that bridge, and something happened to one of these pillars and everything collapsed. So obviously we are losing so much money, we are going to be losing so many lives. That's why it is also important for us to have the N minus survival rule. When we are talking about the organization, about the power organization, when we're talking about different kind of organization, we're also talking about different association. It means that those guys, they have the responsibility to put some laws, to put some kind of regulations for different kind of companies or different kind of clients or maybe the customers in order to make sure at the end of the day everything is safe and sound. One of those associations is called as NERC, because the North American Electricity Reliability Corporation. So those guys has this responsibility to put the rules, the restriction and regulations for us as the companies that are going to also observe or study other people's work. By other people, I mean the clients, which is the clients means the high amount of loads or the massive loads or the massive generational part, to make sure that everything is safe and sound. So as they said, the grid must, this N-1 or the contingency rule is one of their criteria. They would say that the grid must survive the sudden loss of any single piece of equipment, something we call as N-1. By the way, in N-1, we are only going to lose one equipment at a time. We also do have other kind of contingency tests or other survival rule tests. We call that N-1 means that 2 equipments at a time, but let's just make it simple. So without dropping power to anyone, we are going to build the massive reserve margins and transmission headrooms just to sit empty, waiting for disaster. What does that mean? It means that imagine that you do have this kind of bridge, and this bridge has 3 pillars itself. Maybe those 2 pillars from the beginning to the end, those 2 guys are going to act so fine, and we don't have any problem 99% of the time of the year. But at some point, something happened to one of those pillars, and we need a backup system. So backup system is just there. We pay millions of dollars. That guy is just there to just for that 1% of the year. So if something happened to any of these guys, we are going to make sure that millions of people are not going to lose their power, they're not going to lose their businesses, they're not going to have, and we are not going to have any damage because of this, some kind of grid reliability or the power reliability to their some kind of devices. So that is also a very important part that I want to talk about it. Then another thing that we have to know is about the simulation chaos. So as I just told you, just forecasting, just knowing about something is not very useful. We also have to simulate something. And why we're trying to simulate that? Because obviously when a client comes to us and say that, hey, I do have the generator and this amount of megawatt, I would like to connect it to the system, we say that, okay, build it, come back to us, and then we can connect it to the system. If something happened, you go back and fix it. Obviously, it's not feasible because it takes time, it takes money, and no one likes it. Because at the end of the day, imagine you paid 10 or maybe some kind of $100 million because all of those equipments that you're building, obviously the transmission line and any upgrade that you would do to the system, and at the end of the day, you say that, okay, sorry, we cannot do that. So who is going to be liable for all of those compensations? That's why at the beginning of the work, just before doing any kind of thing or before lifting some kind of cable or wire or doing any labor job, we just ask the clients to give us some kind of model. They're kind of, we call it as a PSCAT and PSSE model, which I'm going to talk about. What are those softwares? We just ask them to give them this simulation model. Imagine that before building your motor, before just kind of building anything in the 3D printer device, first, you're going to look at your blueprints or look at some kind of architecture in your computer to make sure that everything is fine, you don't have any problem. And then you're going to do the printing job. And also, when you're doing the printing job, you're not sure 100% that the product that you have at the end of the day is going to be as the same as your blueprint. So you have to compare those values, or you also have to compare something and do some kind of a little bit of adjustment to make sure at the end of the day, your final product is going to be as the same as the blueprint. This is something that we also do. We are not only going to give a thumbs up to the client and say that, hey, you can make this one because we did the study, we did the forecasting, everything is fine. After a couple of years, when the customer built that valve, built that specific thing, a specific material, it could be a generator, it could be a load, it could be anything, they also have to come back to us. That we call something as a commissioning phase. So in this commissioning phase, we are going to compare the values of their actual or the physical machine to the one that we had before. For example, right now they give us a model in the software and say that okay, everything is fine. Then they're going to build something, and after that they come back and say that okay, give us the commissioning information or the data set. And then we are going to compare those values with what? With the software values. And when we say that everything is okay, is based on your promise, with a little bit of tolerance, we say that okay, now you can connect yourself to the grid. So it is very important. So the very first thing that we have to know about the system or the normal system is something that we call it as steady state load flow. It means that the system works normally, works fine for days, for years, for hours. So you don't have any problem. This is something that we call as the normal mode or the everyday mode. Another thing that we have to consider is a transient stability. What does it say? Imagine that you do have a car and your car is just running and is just some kind of moving and you're driving it with 100 kilometer per hour. Obviously, your car wasn't at 100 kilometer per hour all the time. Your car, it started from the 0 kilometer per hour, you had your some kind of pedal, and then it takes some time to reach that 100 kilometer. Obviously, it is not going to also stay at 100 kilometer per hour. You're going to have some bumpy road, you have to use the brakes and so on and so forth. But at the end of the day, you would like to make sure you're going to reach your destination. This is something that we're also talking about the grid planning. This is something I've talked about the power engineering, because when we generate something, when we generate the power, we would like to make sure that at the end of the day, we are going to reach to the value that we like, which is called as a steady state. But reaching to that value takes time, from a couple of milliseconds to seconds. So those process from reaching to zero to the value that we like is called something that we call as the transient stability. And we also have to make sure as a transmission planner that we are dealing with those generators or loads, they're not going to violate anything. They're not going to cause any issue, because it's not just only about the beginning of the part. At some point, you're going to have some fault on your system, and you will like to make sure that your generator is not going to cause any issue again. Your generator is not going to be faulty and disconnected, because obviously at the end of the day, if one generator fails, it means that system can handle that. But imagine that two generator fails, and if two generator fails, it means that your pillars from the bridge is gone, two of them are gone, and two is a very severe condition, and all of those other pillars were gone as well. This is something that we call as a cascading blackout. Because of one or two generations, or maybe one or two not proper functional components in your system, everything collapses. And obviously we don't like it, right? Another thing that we just talked about the contingency analysis, which means that we do have one faulty component at a time, but at the end of the day, we would like to make sure because of that one faulty component, the whole system is not collapsed. And another thing is going to be voltage stability. It means that when we are talking about the 60 hertz, when we are talking about, for instance, 120 volts, we would like to have it all the time, right? So another thing that we have to see is that as a transmission planner, or even every other job, we have to see the constraint. We have to see the choke points. It means that this simulation, the software that I told you about, is some kind of these two softwares, PSSE and PSCAD. You all can some kind of research it, but this is not my main concern. I'm just giving you a little bit of heads up. So we do all of this simulation to find those constraints. One of the important constraints is about the thermal limits. It means that obviously wires, they cannot handle that amount of whatever amount of voltage you like. They're going to have some issues. So it means that when you're dealing with a system, when you're dealing with a generational part that is going to produce so much amount of voltage, or you have a load that is going to consume so much amount of voltage, we need some upgrades. Another thing that we have to see is about the voltage limits, because the pressure is going to dropping too low or spiking too high. It means that because of some factors inside our transmission planning system that we are going to talk about in detail in the power system, we are going to have two major issues. Either we do have the under voltage, or we do have the over voltage. So these kind of problems is also going to cause for other part of our system, other part of the infrastructure that we don't like to have them. And finally, we talked about stability limits. It means that at the end of the day, as I just told you, the amount of power that we're producing should be as the same as the amount of power that we are consuming by considering the power loss itself. And then when we learn about all of these studies, when we learn about this limitation, we have to what? We have to level up the grid. Leveling up the grid means that at this point we found out that this amount of cable or this number of cables or this number of generation is not high enough. So we need more. It means that we have to spend millions of dollars to what? To produce those assets to make sure at the end of the day everything is going to be trustworthy. Those things could be the new lines. It means that I do have, for instance, a new load, and for that new load I have to make a new line or new connection. It means that the line upgrades means that, for instance, at this point I know that this line cannot handle the 25 kilovolts of voltage that goes past through itself, and I have to upgrade it to 69 kV. Rather than that, my line is going to be melted because of all of those heat that this amount of current is going to have. The power loss is all the time there. This is something that you cannot ignore. Then we do have the energy storage. It means that at some point, the amount of energy that I'm giving to the system is not high enough. Or at some points, in order to make sure that my system is going to pass those bumpy roads with something we call as a transient stability, we need some energy storage. It could be like batteries, it could be like kind of reservoir, it could be anything. Then we do have the demand response. The demand response means that the amount of generation should be as the same as the amount of consumption. But at some point, generation is not high enough, and we have to make sure that the facilities, that some kind of industrial facilities, are going to manage or scale their loads, because at the end of the day, we would like the commercial loads, which is going to be us as a human. We do have all of the power that we need. And finally, we do have different kind of devices that we call as FACTS. What are FACTS? FACTS are flexible AC transmission systems, which is going to like as the capacitors or inductors. If you guys remember, or maybe you guys are going to be familiar, the one thing that I mentioned from the beginning of the part was that voltage has high reliability to what? To the reactive power. It means that if reactive power is not high enough, means that we do have the under voltage issue. And if the power factor is high, we do have over voltage issue. In order to manage this amount of compensation between the under voltage and over voltage, because generation is something constant, we don't have that much of a control over it. But at some point, something will happen, and we do have temporary under voltage or over voltage issues because of the loads itself. In order to manage that, we are using the FACTS devices. FACTS devices are very different, but two important concepts are going to be the capacitors, and they're going to be what? Inductors. Capacitors, these guys are going to what? Are going to inject the reactive power, while inductors are going to consume the reactive power. So at some points, if we do have the under voltage issue, I need the capacitor. When I install that, the reactive power will be high, and then I do have more amount of voltage, so I'm okay. And at some points, when I do have the over voltage issues, it means that at some point, there's some part of or some portion of reactive power should be consumed, so we do have inductors. These guys are some kind of very high speed that they can some kind of have some capacity boost. And what at the end of the day, what is the juice? Juice is the reactive power. So a final thing that we have to talk about is the clear energy, some kind of fun loss. So when we are talking about the clean energy from the perspective of a normal person, we say that, okay, let's just install all of those renewable energies to the system. Let's install or let's spend millions of dollars on renewable energies like the wind, solar, whatever we have, and connect it directly to the grid. So at the first point, it would be some kind of make it very logical, right? We say that, okay, we do have so much amount of wind, we do have some kind of amount of sun over here. Let's try to make as many as possible and try to increase the capacity of our generation. Why? Because at the end of the day, we could get rid of all of those fossil fuels. One thing that we have to consider, and most of the time is something that we neglect, is something we call as inertia. What does it mean, inertia? Imagine that you do have your car, and your car obviously takes some time to reach to the speed from 0 to 100 kilometers per hour. So at some point you would say that, okay, I don't like it. But at another point, it has some privileges. It means that if you're in a bumpy road, if something happened, and if you put your some kind of foot on a brake, your speed is not going to reduce that much, right? Because at the end of the day, if your speed reduces so fast, imagine that you're 100 kilometers per hour and then you reach to the zero. It's not very feasible physically and from the Newton laws. So It means that this guy is going to give you the privilege against fighting the bumpy road. Imagine that we are going to replicate that concept to the grid itself. That you do have a system and it's working with 60 hertz and you do have it at 120 volts, but something would happen because of the fault, because of any issue in your grid, and then your some kind of power would reduce. So this reducing power means that something happened to your generators. But in generators, the good thing that the past ones has, that they had the high inertia. It means that because of the issue that happens in any part of the grid, my system is not going to collapse so fast. Those guys were physical machines. They had inertia, and those inertia, even for a couple of seconds, could help me in order to get rid of that fault. Because most of the time, the faults are not going to be there all the time. They're just there at maximum of a couple of milliseconds or maybe 10 seconds. So if we can get rid of that, and if I do have amount of backup for myself, we call it as inertia, that is going to be produced by all of those power generators and those massive flywheels. So I'm okay. But imagine that right now we are shifting towards renewable energies. Renewable energies they are going to replicate the work of those massive flywheels. They're just electronics. They are going to convert the amount of power. They do have the wind turbine. They're going to have some kind of gear part. Then we do have the voltage using the transformers, and then so on and so forth. But what would happen to my system that if those renewable energies, which means that, for instance, solar doesn't have any inertia, right? Solar is just there or not. I mean, obviously there's a number between, but it means that if it stopped, it is stopped. There is not anything that can some kind of help me to the system. Imagine that I do have the bumpy road, but my power generation or my motor, which is going to be motor of the car, by the way, is so fragile that by any problem that motor stops. So obviously because of just one bumpy road, if my motor stops, how am I going to reach to my destination? This is the huge issue that we do have right now with renewable energies, that they do have the low inertia. That's why in some kind of as a transmission planner, we also have to make sure that our system has not very high inertia, but it has a feasible amount of inertia that could manage different kind of faults. We are going to connect our client's model to the system, which we are going to consider as the total grid, and then by adding those different kind of faults, maybe at some point 300 to 400 faults, different kind of faults. By the way, when you're talking about faults, not all of them are going to be three-phase or single-phase. We do have different kind of faults, or different kind of situation or condition changing in the grid itself. So we are going to add those faults and make sure that system is okay. Then we can say that, okay, thumbs up, you can move forward. So this is very important. So next time, if someone talks about the renewable energy generation, and they said, okay, let's just naively connect anything that we do have to the system, at least you have some ideas in the background that why we cannot do that. So, and another step that I just talked about it was about the show me the money part. It means that obviously when we do have all of those studies, when we do have all of those some kind of massive outcomes or conclusions from our work, we do have some kind of cost, right? Okay, just building those lines are not going to be very cheap. I mean, building per mile of those cables could cost from $2 to $5 million, because it's not just about those lines. It's about all of those protection parts that we have to consider for the lines as well. That's why it means that the amount of cost. So why we're spending that much amount of money? Because we would like to reach the benefits. What is the benefits? We do have the clean air. We do have no problem with outage. We don't have some kind of any problem with the economic boom or increasing the number of people, and we are going to be safe and sound. So another important thing that we have to say is that in this game, we are talking about a couple of years or maybe decades of prediction. So everything is not going to be happen in one night, and it's not going to be happen fast. It means that an issue could happen for a couple of milliseconds or microseconds. But this kind of building an infrastructure to stop that small issue could take from 7 to 10 years, 7 to 14 years, or maybe more than that. So 1 or 2 years is about the planning studies. It means that it takes obviously time to have all of those studies. We are not going to sit beside the computer and hit the run and everything happens so fast. Even those softwares take so much time to some kind of run the studies, run the simulations, because the system is huge. And obviously you cannot just have your system okay by only the first run. You have to have so many adjustments, or you have so many communication back and forth, and it takes amount of time. And then we do have the regulation environment hearing. It means that you have to make sure that everything is okay, because when you say that, okay, I would like to build this amount of system, and not everyone are going to be on the same page with you. We do have problems with the environmental people. We do have all of those, some kind of regulation people. Everything could have impact on your project. And at the end of the day, you do have the construction. If everything goes well, you do have everything that you need. So this is the real world puzzle. We do have the wind corridor. It means that there are wind or any kind of generations. It means that you do have your wind turbines, this massive and huge, by the way, they're huge turbines. That's why I probably put a picture of it, that I recently had a visit at one of those sites. I put it over here and see that how big is that. By the way, I'm 6'6", so you can see that how big that turbine is. And then we do have these massive turbines at some kind of the rural area is going to maybe have 100 or 150 kilometers just outside of the city. Then you do have this massive transmission line, and these massive transmission lines are going to transmit all of those power to your house. It means that we need some kind of upgrades, we need different kind of devices, transformers, and so on and so forth. Then we do have the city boom. It means that the people are moving from the rural area to the city area. It means that the amount of construction, the amount of load that we need for the city is going to increase and increase. Obviously, it means that we have to increase the number of generation. And then we do have another problem. And the problem is actually transition from the coal to solar, or the coal to wind. Because what? Because all of those greenhouse gas emissions, we would like to have the clean air, we don't want to have the pollution. That's why we are moving from the past way of generation, which was feasible, which was easy, but obviously on another hand has some kind of issues and drawbacks for us. And all of these things side by side with each other is going to make a transmission planner job very important. So at this chapter, I just talked about my day-to-day life job that I'm actually doing. Obviously, it contains so many of details and so many meetings, some kind of, again, learning, because as I just told you, I just started this job. And obviously, at the end of the day, when you see that, when you understand that how much impactful your job has for other people's day-to-day life, say that, okay, I'm actually doing something. So again, if you had any questions related to my job, just try to comment it. I'm trying to answer as much as possible. But again, that was the very first chapter of the power systems. So in power system, right now, we do have a very good idea and analogy that why actually we're talking about those, why we're talking about active, reactive power, how actually you're going to use that. And I'm trying to some kind of share with you guys everything that I learned at my work, and after that you guys can see that, okay, why they actually learning the power systems in some kind of academic lifestyle, especially for the people that actually would like to have this job or have a job like this, because obviously this is not the only job. But my name is Mahmoud Kiasari. Thank you for watching this video. Have a super great day, night, whatever. See you around.